Now that we're getting into new material, I do plan to slow down a little bit and start reviewing more material if I feel like my explanation got a little bit quick. Remember that last time we derived the Clapeyron equation, and remember why it's useful. The Clapeyron equation says that dp star, or dp set is how the book says it. Again, I try to use the notation of the book, but I like the star notation a lot better. dp set dt is equal to delta H of vaporization divided by T times the molar volume of the vapor minus the molar volume of the liquid. So this is an equation that relates the slope of a curve of P set by T. So that curve would look something like this. Remember, on the phase diagram, probably looks something like this. This dp set dt is the slope of this line here. This is the vapor-liquid equilibrium line. Recall again that this is the critical point. So if I label my phases, I've got solid phase. I have to label my axes too, P star and T. Solid, liquid, vapor, and then beyond the critical point, beyond that horizontal, I have supercritical fluid. All right, so what we're trying to do is model the slope of this line. So remember, if we have a phase diagram, we don't have any need for the Clapeyron equation. All we need is simply to look up the value of temperature, and we could find the corresponding value of P star. So if this is T1, I just simply go to my phase diagram and I look at it. Again, the idea here is that we are not always going to have a phase diagram for any chemical we want, and we definitely don't have a phase diagram for any mixture of chemical that we want. So recognize how the Clapeyron equation could be difficult to use. The first thing is that it assumes that we have at least one data point with which to work. So it assumes that we've done one experiment and we know at least one data point. Must know at least one data point. Because we have to have a starting point to work off of. Because this is a curved line, where the slope is not going to be straight. It's going to be different everywhere. So we have to have a starting point with which to work, and then for a given change in temperature, we can model it as linear. That's how we get into the Clausius-Clapeyron equation. So part of the problem with the Clapeyron equation is that delta H vap is not necessarily known. I'll say it's not necessarily known as a function of T. F of T and P star. So in general, the enthalpy of vaporization will change depending on what your conditions are. And also, it's not necessarily true that you know what the molar volumes are. So you could measure them if you want, or you could model them, right? So you could model the molar volume of the vapor with an equation of state, or the molar volume of the liquid if you have an equation of state that models both equivalently well. But again, you don't necessarily know which equation of state you should necessarily use. So last time that inspired a guy named Clausius to come along and modify the Clapeyron equation. And remember, the assumptions of the Clausius-Clapeyron equation was that delta H vap is constant. And therefore, when we integrate this, we can pull this delta H vap out of the integral. Clausius also assumed that the molar volume of the vapor is much, much greater than the molar volume of the liquid, which is a pretty good assumption. Again, because vapor takes up so much more space than liquid, the molar volume of vapor will always be, well, I won't say always, at room conditions definitely, the lower the temperature is, the more true this is. But as temperature starts increasing, the liquid starts taking up more space and the vapor starts taking up less space. And these two things get closer and closer together until at the critical point, there shouldn't be any difference between the molar volume of the vapor and the molar volume of the liquid. And the third assumption is ideal conditions. Ideal such that the molar volume of the vapor is equal to RT over P star. And then plugging all those assumptions in and then integrating this equation gives us the Clausius-Clapeyron equation. And Clausius-Clapeyron is at the ln of p star 2 over p star 1, or p stat. Remember, p stat and p star are interchangeable, is equal to minus delta H vaporization over R, 1 over T2 minus 1 over T1. All right, so given values, you have to be given values for enthalpy of vaporization. You have to be given a value of initial temperature and target temperature. You have to be given that one data point. Remember, I said we had to know at least one thing. So we have to know what the vapor pressure is at temperature 1. R is, of course, the gas constant, which you could always look up. So you need to have these 4 pieces of information, and this will allow you to solve for vapor pressure at some given temperature 2 that is of interest of you. Remember, you can only use this Clausius-Clapeyron equation if these 3 assumptions are holding true. And that seems to be pretty restrictive. So I want to go through in this video what to do if one of these assumptions doesn't hold and you cannot use the Clausius-Clapeyron equation. In that case, you would have to go back to the original Clapeyron equation, and you would not be able to pull this delta H vaporization out of the integral, and necessarily you wouldn't be able to make any simplification. So what should we do then? So I'm going to start back with the regular Clapeyron equation. dP star dt is equal to delta H vaporization over, what is it? I don't write this one as often. T molar volume of the vapor, molar volume of the liquid. And I need to figure out what simplifications I can make. So I could substitute in for the molar volume of the vapor and the molar volume of the liquid. However, I'm going to need an equation of state for that. And in the general case, I don't want to specify which equation of state I'm using because that could be different each time. So instead what I'm going to do is substitute in for the compressibility factor. So I'm going to use the definition of Z, and Z is PV over RT. And I'm going to solve for the molar volume for both the vapor and the liquid case. So just by rearranging this, I can say that the molar volume of the vapor is ZRT over P, and this is P star. So this is P saturation, because this equation is assuming that I'm on the saturation curve. And similarly, the molar volume of the liquid is Z liquid RT over P star as well. All right, so I'm going to make that simplification. I'm going to plug all those values in, and I'm going to factor out this common RT over P. All right, so that is going to give me dP star dt is equal to delta H vaporization RT squared by P star, and then I've got a Z vapor minus Z liquid. And then anytime I have a quantity of Z vapor minus Z liquid, or any property of the vapor minus any property of the liquid, I can write that neatly mathematically by saying that it's simply delta Z for vaporization. Because that's what a vaporization property does. It compares the value of a certain property from the vapor phase to the liquid phase, and that tells you what the change is of that property upon vaporization of that substance. Okay, where are we at now? How has this helped at all? It seems like we still have delta H vap, that's a function of temperature and pressure, and we have delta Z vap, that's a function of temperature and pressure. Well, above, I said that the molar volumes at the critical point will be equal. And actually, all thermodynamic properties for the vapor and the liquid converge at the critical point and beyond. So at the critical point, so at critical T and P, we can say that the enthalpy of vaporization goes to 0. And also, right, because that makes sense, right? There is no enthalpy of vaporization beyond the critical point because there is no more phase change. The substance doesn't exist as a vapor or a liquid anymore. It's just supercritical fluid, and they're indistinguishable. So therefore, there is no enthalpy of vaporization. And because they're indistinguishable, we can also say that the change in the compressibility factor upon vaporization also goes to 0 at the critical point. So even though the logic here is that enthalpy of vaporization is changing with respect to temperature, and if we had a mathematical model, if we had an equation that says that enthalpy of vaporization were like some constant times the temperature, we'd simply plug that in, and then that temperature dependence would be taken care of for in the integration. But we don't have a mathematical equation for that, so we can't do that. Same thing for z. We know that it's a function of temperature. We don't necessarily know what the function is. Therefore, we can't plug it in and take care of it that way. What we can do, however, is use this fact and couple them together and say that if the enthalpies of vaporization and the compressibility factor are both going to 0 at the same point, we can say that the ratio of delta H vaporization divided by delta Z of vaporization is constant, even though neither property is constant by themselves. Right, so say at T1 and P1, delta H vap has a certain value, delta Z vap has a certain value. Whatever those values are, we're going to assume that they change roughly the same as they both go to 0 at the same point. And then that fact is what is going to enable us to pull this value out of the integral. So we can integrate this now. So I've got dP star over P star is equal to delta H vaporization over R delta Z vaporization. And then it's going to be integrated. I've got a 1 over T squared left over dt. We're going from T1 to T2 and P star 1 to P star 2. That is going to give us something that looks very similar to the Clausius-Clapeyron equation. So we're going to have ln P star 2 over P star 1 is equal to delta H vape over R delta Z vape, minus out front coming from this integration, 1 over T2 minus 1 over T1. All right, so this one doesn't really have a name. I call it the modified Clausius-Clapeyron equation because if you compare it to the Clausius-Clapeyron from before, right, it looks very similar. The only thing is that I'm inserting a delta Z vaporization in there. I also want to note that if you start with this equation, the modified Clapeyron equation, and you say that later on you assume ideal, right? So at ideal conditions, your pressure is probably low and your compressibility factor for an ideal gas, so Z is equal to 1 for ideal gas, and also Z is equal to 0 for incompressible liquid. All right, so if you have both of those, delta Z vaporization is 1, and that can simply just cancel out, and you're left with Clausius-Clapeyron again. All right, I want to talk about one other equation that made a cameo in material and energy balances. That is the Antoine's equation. So Antoine's equation is an alternative to either one of these two. So we've got four equations if you count the modified Clapeyron equation. I guess the Clapeyron equation is not really usable for the most case. So you've got Clausius-Clapeyron, this modified Clapeyron, and Antoine's. And Antoine's is, again, something that should look familiar to you from your MEB days. It says log base 10. I'm going to try and keep my pen convention consistent. Log of P star is equal to A minus B over T plus C. Remember that A, B, and C are Antoine's constants. You need to look those up in a table or a source. Antoine's constants, A, B, C. You also need to reference your particular source to see what the units of T and P star are. So that is very important. Units are set by your source table. So every single table that has Antoine's constants will tell you vapor pressure has to be in bar or PSI or whatever, and temperature is in Celsius or Fahrenheit or Kelvin or whatever. Importantly, temperature does not automatically have to be on an absolute scale here. So T, not necessarily absolute. The moral is to use your source table all the time, not necessarily absolute scale. This is one of the only engineering equations I know that uses temperature that doesn't necessarily have to be on an absolute scale. Also, your table may say it's ln here too. So maybe ln here instead of p star. And again, that just depends on the table. Whatever Antoine's constants that you have given by the table, you want to use that form of the Antoine's equation for which they were fit. The other thing to know about Antoine's equation is that it's purely empirical. So this one is purely based on observation, on experiment, observation. There is no fundamental basis for this. In other words, I can't start with something that I know, like above the Clapeyron equation starts by saying that the Gibbs energies for the vapor and liquid phases are equal and goes from there. There is no such origination point from Antoine's equation. It just seems to come from nowhere. But the idea is that it is a curve fit. So it is simply an empirical curve fitting operation. So there's three parameters that are fit to whatever this line is. So this vapor-liquid equilibrium line is set by those three parameters. And then from there, the calculation is pretty easy. You just look up the Antoine's constants. If you know the value of t that you're trying to find the p star, you plug in everything and you calculate your p star, or vice versa. All right, so just to wrap up, these three equations are useful for being able to estimate vapor pressure as a function of temperature. However, you should recognize that these are all estimations and they're not very mathematically rigorous. So they're good for getting you introduced to the topic. They're good for if you need an estimate ever, but they're not so good if you need specific calculations and you want to have a high degree of precision. So for that, we're going to need a little bit more rigorous of a mathematical model, and that will be the topic in the coming videos.